So we don't have a whole lot of mechanical math to do today. We're not going to learn a lot of specific techniques. Instead, we're going to introduce the two big questions that we're going to spend the first half of this course solving. And we'll learn that actually these two questions are very similar. They're really the same question, just looked at through different viewpoints. So today we're going to get a conceptual understanding of the first half of calculus. It takes me 15 minutes to go through that conceptual understanding, and then it's going to take the rest of the next month and a half to actually work through the details of what we're talking about and to look at all the ramifications of what it means once we've answered these two questions. Okay? So the first question that we want to talk about is the linearization problem. Okay? And we do this in lots of ways in our interactions with the real world. We take things that are nonlinear and we try to zoom in on them in such a way to make them linear. Okay? One example I can think of is that as I'm standing here on the curved surface of the Earth, we all feel that it's flat. Okay? We know that we're standing on a sphere, but we feel that it's flat. Why? Because we're zoomed in close enough that flat is a good enough approximation to this curved sphere. So the basic idea is this, right? So if we want to approximate this blue curve with a line at a point, we can do so by drawing what's called the tangent line. And the idea is if we were to zoom in where the tangent line is intersecting this curve at that point, we see as we get closer and closer, notice that, well, the red line starts out not being anywhere close to that blue curve. As we zoom in, the red line is a very good approximation for how the blue curve is behaving. So that's our first topic that we want to talk about. How can we linearize something that is nonlinear? Okay? If you think about it, the very first skill you learned in algebra was how to solve linear equations. We know all about them. They're easy to work with. Okay? So that idea is going to be the first one we want to address. Okay? Under what circumstances are we able to zoom in like this? We won't be able to do this in all cases. Calculus doesn't solve all of our problems, it just solves a lot of them. Once we know that we can zoom in like this, how do we actually do that rigorously? I mean, this blue curve, we can see it because I drew it on the board, but what about more abstract functions? How would we do that? How can we do that rigorously and mathematically? Even this idea of zooming in, how do we encapsulate that idea of zooming in mathematically? So that's the first thing we're going to look at. The second problem is the instantaneous rates of change problem. Okay? How do we determine the instantaneous velocity of something? So for example, here we've got the good old Leaning Tower of Pisa, which is entered into mythology as the tower Galileo dropped a ball off of. I don't think he did that at all. Okay? But regardless, we drop the ball off the Leaning Tower of Pisa and it falls, right? And it falls this much. I don't know how tall the tower is. It falls this much in a certain fixed amount of time. Okay? We can always come up with the average rate of change. Okay? We can always find the average. And we'll see how to do that. We'll review how to do that in just a moment. We can always compute an average rate of change, but my question to you is, after this ball has fallen for 1 second, at t equals 1, how fast is that ball traveling? Not what's its average velocity over the course of the fall, but at the time t equals 1, how fast, what is its speed? What is its velocity? Okay? I'm not going to be very careful about the word speed versus velocity yet. When we get into some story problems later in the course, I'll be more careful. So these are two completely separate questions. Now let's talk about this. I want to talk a little bit about the instantaneous velocity problem for just a second. So let's say we want to drive from here to Santa Fe. Okay? I don't know. I'm kind of new to the area. How far is it from here to Santa Fe? Does anyone know?
6 hours.
6 hours? How about a distance? Can we call it 300 miles? Does that sound about right? That's too short? Let's call it 400 miles? 400 miles. Okay, let's say it's 400 miles. We're going to say it's 300 miles because it works a little easier with the numbers. Okay? Let's say it's 300 miles from here to Santa Fe. Okay? And let's say it takes us 6 hours. Okay, so we travel 300 miles 6 hours. Okay? Well, I could ask the question, how fast were we going? We traveled 300 miles in 6 hours. What's that?
50 miles an hour.
So one way to answer the question is to say that we traveled on average 50 miles per hour, right? So we can always compute the average velocity by saying what is our total distance, and I'll be a little more careful, total displacement over total time. Well, in this problem, we were displaced 300 miles over a time of 6 hours, which gives us 50. Let's look at the units on this. What are the units on 300? Miles. What are the units on 6? Hours. And in English, how do we read the division bar? Per. Right? So what are my units on this? This is 50 miles per hour. So that is a rate of change. Okay? As it tells you how your miles changes as time changes. Okay? Well, I'd like to look at this problem just a little bit differently for just a second. Okay? Let's go ahead and graph our time on the independent axis and our displacement on the y-axis. Okay? So at some point after it's been 5 hours, we've traveled a distance of 300 miles. So we're up here. This is the ordered pair 5, 300. Okay? And where did we start? Well, we started here with a time of 0 hours. We started the stopwatch at 0. Okay? And we started at a distance of 0 miles. Okay? Now, if I were to describe the motion that we take, maybe driving from here to Santa Fe, I don't know, maybe it looks something like this. Where the steeper the curve, the faster we were traveling. Okay. Well, what could we always compute? I can always compute this dashed line right here. And what is the slope of this dashed line?
300 over 5.
It's 300 over 5, right? So 300 over 6, excuse me. It's 300 over 6, so it would be that 50 miles. The slope of this line is 50. I can always compute my instantaneous rate of change. Excuse me. I'm sorry, I said that wrong. I can always compute my average rate of change. What can I not always compute? Instantaneous rate of change. Okay? So I could find the slope of this line, but I don't know how to talk about what our actual velocity is at points in time. What could I do? Well, in a car, you do have a speedometer, right? That's telling you how fast you're going at any instant. But even that is really just an average, right? It's taking some data from how how quickly your wheels are spinning, and it's computing a very tiny average, but it's an average nonetheless. How do we actually get an instantaneous rate of change? Well, what do we even mean by an instantaneous rate of change? I think we all have a general sense of what that should mean, but we're not even sure how to define it maybe at this point. Okay? So that's the next question we want to ask. How do we calculate an instantaneous rate of change? And I did say a moment ago, I said, well, it seems like these two problems are completely different. Turns out our methods for solving these two problems are exactly the same. And in fact, these two problems are almost identical.